Picture this scenario. You're tracking what appears to be a routine interstellar comet racing through our solar system at breakneck speed. Everything looks normal until you start plotting its trajectory with mathematical precision. The numbers don't just show a random cosmic flyby. They reveal something that makes seasoned astronomers do double takes at their calculations. 3. I/ATLAS isn't just passing through our solar system. It's following a path that brings it unnervingly close to Mars on October 3rd, 2025. Close enough that some researchers are quietly asking questions they don't want to voice publicly. Questions about whether this ancient wanderer from another star system might be doing something far more deliberate than anyone wants to admit. Tonight we're diving deep into the orbital mechanics that have some scientists scratching their heads and others losing sleep. Because when you run the numbers on 3 I/ATLAS, when you trace its precise path through space and time, something extraordinary emerges. This isn't your typical random interstellar visitor following the chaotic trajectories we expect from cosmic debris. This is an object whose approach to Mars falls within statistical parameters that challenge everything we thought we knew about celestial coincidences. My name is Marcus, and I've spent the last 15 years analyzing orbital dynamics for objects that shouldn't exist according to our current understanding of physics. What I'm about to show you represents months of detailed mathematical analysis, cross-reference from observed with data aeries worldwide, verified by independent calculations that all point to the same unsettling conclusion. 3 I/ATLAS exhibits navigational precision that transcends random chance. But before we unpack the mathematics that's keeping researchers awake at night, let me tell you exactly what we're dealing with. On July 1st, 2025, Chile's Atlas telescope detected something extraordinary racing toward our solar system from the direction of Lynx constellation. The object designated 3 I/ATLAS moved at velocities that immediately marked it as interstellar in origin. Not bound by our sun's gravitational influence, not following elliptical orbits like solar system natives, but tracing a hyperbolic path that could only mean one thing. This visitor came from another star system entirely. The initial excitement focused on its chemical composition. James Webb's Space Telescope spectroscopy revealed carbon dioxide concentrations unlike anything we'd seen in previous interstellar objects. Hubble captured images of its distinctive coma structure. Ground-based observatories worldwide coordinated tracking efforts. Everything appeared to follow standard protocols for studying cosmic visitors. Everything except the trajectory itself. Here's where the mathematics become disturbing. 3 I/ATLAS approaches Mars at a distance of approximately 30 million kilometers on October 3rd. In cosmic terms, this represents an extremely close encounter. Close enough for detailed gravitational interaction, close enough for potential orbital modification, close enough to trigger questions about whether we're witnessing natural celestial mechanics or something far more sophisticated. The statistical probability calculations paint a picture that challenges conventional thinking. Random interstellar objects arriving from arbitrary directions in space should exhibit trajectory distributions that reflect the chaotic nature of their ejection from distant planetary systems. They should approach our solar system from angles that represent the statistical randomness of galactic dynamics. They should not demonstrate the kind of precision targeting that 3 I/ATLAS displays in its approach vector toward Mars. Dr. Elena Rodriguez at the European Space Agency's Advanced Concepts team ran Monte Carlo simulations modeling 10,000 randomly ejected interstellar objects entering our solar system. The results show that fewer than 3% of such objects would achieve approach distances to Mars, comparable to what 3 I/ATLAS will accomplish. Fewer than 1% would time their arrival to coincide with Mars' orbital position for optimal gravitational interaction. The mathematical odds of 3 I/ATLAS achieving both parameters simultaneously through pure chance, hover around 0.05%. These aren't the kinds of numbers that make astronomers comfortable. These are the kinds of numbers that suggest either we're witnessing an extraordinarily rare cosmic coincidence, or we're observing something that operates according to principles we don't currently understand. The trajectory analysis reveals additional anomalies that compound the mystery. Most interstellar visitors detected to date have approached from directions roughly perpendicular to our solar system's orbital plane. This makes sense given the random nature of their ejection mechanisms from distant planetary systems. Objects flung into space by gravitational interactions with giant planets or stellar encounters should arrive from essentially random directions distributed across the celestial sphere. 3. I/ATLAS violates this expectation. Its approach angle demonstrates alignment with our solar system's ecliptic plane that falls within 5 degrees of optimal for energy-efficient trajectory modification. This alignment maximizes gravitational interaction potential while minimizing velocity changes required for significant orbital alterations. The mathematics suggest either unprecedented cosmic luck or deliberate navigation planning. NASA's Jet Propulsion Laboratory confirmed these calculations using independent orbital determination software. Their trajectory reconstruction shows 3 I/ATLAS following a path that intersects Mars' orbital zone at precisely the moment when gravitational influence can achieve maximum effect with minimum energy expenditure. The timing represents optimal efficiency for any hypothetical course correction maneuvers. Dr. Sarah Chen, who leads trajectory analysis for potentially hazardous asteroids, admits the numbers make her uncomfortable. Her team routinely calculates approach parameters for thousands of solar system objects. Never before have they encountered trajectory precision comparable to what 3 I/ATLAS demonstrates. The mathematical elegance suggests engineering rather than chance, but the disturbing implications extend beyond mere trajectory analysis. The object's velocity profile reveals additional anomalies that challenge natural explanations. 3 I/ATLAS moves at approximately 61 kilometers per second relative to our solar system's motion through space. This hyperbolic excess velocity places it among the fastest interstellar objects ever detected. Such extreme speeds typically result from violent ejection processes involving close encounters with massive stellar objects or catastrophic disruption events. However, spectroscopic analysis reveals chemical signatures inconsistent with violent processing. The carbon dioxide-rich composition suggests formation in cold outer regions of protoplanetary disks, rather than high-energy environments that would produce extreme velocities. The contradiction between gentle chemical signatures and extreme kinematic properties defies conventional understanding of interstellar object evolution. Advanced computer modeling attempts to reconcile these contradictions through complex multi-body gravitational encounter scenarios. Researchers propose sequences of stellar flybys that could accelerate objects to observed velocities while preserving fragile chemical compositions. The models work mathematically, but require coincidence sequences with probabilities measured in millions to 1 against occurrence. The alternative explanation involves controlled acceleration through mechanisms we cannot currently detect or understand. Propulsion systems operating below our observational thresholds could theoretically produce the observed velocity profiles while maintaining chemical composition integrity. Such systems would represent technology far beyond human capabilities, but within theoretical possibility for sufficiently advanced civilizations. Ground-based radar facilities have attempted to detect artificial electromagnetic signatures that might indicate technological components within 3 I/ATLAS. The Arecibo successor arrays and Deep Space Network installations conducted coordinated listening campaigns during the object's approach phase. Results show only natural emissions consistent with sublimating cometary materials interacting with solar radiation and magnetic fields. The absence of obvious technological signatures doesn't eliminate artificial explanations entirely. Advanced camouflage capabilities could theoretically mask electromagnetic emissions while maintaining perfect comet mimicry. Such deception would require engineering sophistication that exceeds our current detection capabilities by orders of magnitude. Radio telescope surveys conducted by SETI Institute researchers found no coherent signals emanating from 3 I/ATLAS across frequency ranges spanning potential communication bands. The silence aligns perfectly with natural comet behavior, but cannot definitively rule out more subtle forms of information transmission, operating through mechanisms we haven't yet learned to recognize. Visual observations using the world's most powerful telescopes reveal morphological characteristics consistent with natural comet nuclei responding to solar heating. The developing coma structure, asymmetric dust distribution patterns, and brightness variations all follow predictable physical models for volatile sublimation processes. Surface-through-features visible enhanced imaging techniques show irregular topography, typical of gravitational aggregation rather than manufactured construction. Yet the precision of its Mars approach vector continues to challenge explanations based purely on natural processes. The mathematical elegance of its trajectory suggests either unprecedented cosmic coincidence or navigation capabilities that transcend our current understanding of what's possible in interstellar space. As October 3rd approaches and 3 I/ATLAS closes the final distance toward its Mars encounter, observatories worldwide prepare for the most intensive monitoring campaign ever directed toward an interstellar visitor. Multiple space agencies have coordinated observation schedules designed to capture every detail of the gravitational interaction. The data collected during this critical phase may finally resolve whether we're witnessing natural celestial mechanics or something far more extraordinary. The implications of either conclusion extend far beyond academic astronomy into fundamental questions about our place in a universe that may be far more populated and purposeful than we ever dared imagine. The Mars encounter timeline reveals something that transforms scientific curiosity into genuine unease. When you map out the precise moments of 3 I/ATLAS closest approach, the coordination becomes impossible to ignore. October 3rd represents more than just date at random on the cosmic calendar. It marks the exact window when Mars' orbital velocity, ROT, and gravitational influence, conversational alignment G, to create optimal conditions for trajectory modification with minimal energy expenditure. Think about what this means from an engineering perspective. If you wanted to alter the course of an interstellar object using gravitational assistance, you couldn't design a more efficient encounter scenario. The timing places Mars at the precise orbital position where its gravitational field can provide maximum deflection with minimum velocity change required. The approach angle optimizes energy transfer between the objects too. Even the rotational phase Mars during of encounter maximizes gravitational gradient effects. Dr. Michael Torres at MIT's Department of Aeronautics and Astronautics ran trajectory optimization software originally designed for spacecraft mission planning. When he input 3 I/ATLAS parameters into programs meant to calculate optimal gravity assist maneuvers, the results stopped him cold. The object's approach vector falls within 0.2 degrees of the mathematically perfect solution for maximum gravitational efficiency. No human mission planner could improve upon the trajectory 3 I/ATLAS follows naturally. These aren't the kinds of coincidences that happen by accident in the vast randomness of space. These are the kinds of precision alignments that require either impossible luck or deliberate calculation. The mathematical probability of achieving such optimal parameters through random chance approaches, statistical impossibility. But the timeline analysis reveals even more disturbing patterns. The sequence of events leading up to the Mars encounter demonstrates coordination that spans astronomical distances and geological timescales. For 3 I/ATLAS to arrive at precisely the right moment for optimal gravitational interaction, its journey must have been timed with extraordinary precision across potentially billions of years of interstellar travel. Consider the logistics involved. This ancient wanderer began its journey when our galaxy looked fundamentally different than it does today. Stellar positions, gravitational influences, even the structure of spiral arms have shifted dramatically during the eons crossing 3 I/ATLAS, spent interstellar space. Yet somehow its arrival coincides perfectly with Mars' orbital mechanics in ways that maximize gravitational interaction efficiency. The navigation requirements for such precision exceed anything achievable through random gravitational encounters with stellar systems along its route. Multiple course corrections would be necessary to maintain trajectory accuracy across such vast distances and time spans. Natural processes cannot account for the sustained precision required to achieve the observed approach parameters. Advanced propulsion modeling suggests that maintaining trajectory accuracy sufficient to achieve 3 I/ATLAS approach precision would require periodic velocity adjustments measured in mere meters per second, applied across millions of years. Such subtle course corrections would remain below detection thresholds of current observational capabilities while achieving the navigational precision we observe. The technology implications stagger the imagination. Any civilization capable of engineering billion-year interstellar missions with trajectory precision measured in kilometers would possess capabilities that transcend our current understanding of physics and engineering. They would have solved problems of energy storage, materials science, and autonomous navigation that we haven't even begun to address. European Space Agency mission planners attempted to design hypothetical interstellar probe missions capable of achieving 3 I/ATLAS trajectory precision. Their studies conclude that such missions would require technological capabilities at least 1,000 years beyond current human development. The engineering challenges involve not just propulsion and navigation, but fundamental advances in artificial intelligence, materials science, and power generation that may represent centuries of technological evolution. Yet the alternative explanation requires accepting coincidences so extraordinary they challenge our understanding of probability itself. The mathematical odds of 3 I/ATLAS achieving its Mars approach parameters through pure chance rival, winning the cosmic lottery while being struck by lightning during a total solar eclipse. Possible in theory, but so improbable that rational analysis suggests other explanations deserve serious consideration. The velocity maintenance mystery deepens when you examine how 3 I/ATLAS has preserved its extreme speed across interstellar distances. Objects traveling through space encounter resistance from interstellar medium, cosmic dust, and gravitational influences from countless stellar encounters. Over millions or billions of years, these effects should gradually reduce velocity and alter trajectory in ways that destroy navigational precision. 3 I/ATLAS shows no evidence of velocity degradation expected from extended speed suggested interstellar travel. Its current, either impossibly efficient conservation of kinetic energy or periodic acceleration to compensate for losses during its cosmic journey. Natural processes cannot account for such perfect velocity maintenance across the timescales involved. Theoretical physicists have proposed exotic explanations involving dark matter interactions, modifications to general relativity, or unknown physical processes that might preserve velocity during interstellar travel. These proposals require fundamental changes to our understanding of physics that would revolutionize science if confirmed. The alternative involves accepting technological explanations that challenge our assumptions about intelligence and engineering capabilities in the universe. The chemical composition analysis adds another layer to the mystery. 3 I/ATLAS exhibits carbon dioxide concentrations that suggest formation in specific temperature and pressure regimes found only in outer regions of protoplanetary disks around certain types of stars. The precise chemical ratios observed provide fingerprints of formation conditions that existed billions of years ago around stellar systems we cannot identify. This chemical archaeology reveals 3I/ATLAS as a messenger from ancient stellar neighborhoods that may no longer exist. The parent star could have evolved through its entire life cycle, swelling into a red giant and eventually exploding as a supernova, while 3I/ATLAS continued its billion-year journey toward our solar system. We may be examining the last remaining evidence of planetary formation processes that occurred before our Sun ignited nuclear fusion. The preservation of such ancient chemical signatures across cosmic timescales presents its own puzzles. Interstellar radiation should gradually alter surface compositions through photodissociation and cosmic ray bombardment. The fact that 3I/ATLAS retains clear chemical fingerprints of its formation environment suggests either exceptionally efficient preservation mechanisms or relatively recent departure from its origin system. Spectroscopic monitoring reveals chemical evolution patterns as 3I/ATLAS approaches the inner solar system. The carbon dioxide-rich coma develops asymmetric structures that follow predictable thermal models for comet behavior. Yet embedded within these natural processes are subtle anomalies that continue to challenge conventional interpretation. Dr. Lisa Park at the Harvard-Smithsonian Center for Astrophysics identified emission line ratios that don't quite match standard comet chemistry models. The deviations fall within measurement uncertainties, but they consistently trend in directions that suggest either exotic formation conditions or post-formation processing through mechanisms we don't currently understand. These chemical anomalies could represent natural variation in interstellar object composition, reflecting the diversity of formation environments around different types of stars. Alternatively, they might indicate artificial modification through technological processes designed to enhance preservation or alter observable properties for purposes we cannot determine. The isotopic ratios measured in 3I/ATLAS volatiles provide additional clues about its origin and evolution. Deuterium to hydrogen ratios suggest formation in cold outer disk regions where isotopic fractionation processes concentrate heavy hydrogen isotopes. The measurements align with theoretical predictions for comet formation around solar-type stars, but with subtle variations that hint at different stellar environment conditions. These isotopic signatures serve as cosmic DNA, preserving information about nuclear processes, chemical evolution, and environmental conditions present during 3I/ATLAS formation billions of years ago. The data represents our first direct sampling of materials from ancient stellar systems, providing insights into galactic chemical evolution that complement but cannot be obtained through conventional astronomical observation. As the Mars encounter approaches, these chemical and physical mysteries converge into questions that transcend academic astronomy. Whether 3I/ATLAS represents natural cosmic evolution or something more purposeful, its study provides unprecedented opportunities to understand processes that operate across galactic distances and geological timescales. The next phase of observations during the Mars flyby will test every theory about 3I/ATLAS origin and nature. The gravitational interaction will either confirm natural celestial mechanics or reveal anomalies that force us to reconsider fundamental assumptions about what's possible in our cosmic neighborhood. The gravitational physics of the Mars encounter reveals something that makes veteran orbital mechanicists question decades of experience. When 3I/ATLAS passes within 30 million kilometers of Mars, it won't just be flying by our neighboring planet. It will be threading through a gravitational needle with precision that defies explanation through conventional celestial mechanics. Dr. Patricia Valdez at Caltech's Jet Propulsion Laboratory has calculated gravitational interaction models for thousands of asteroid and comet encounters over her 20-year career. She's never seen anything like what 3I/ATLAS will experience during its Mars flyby. The mathematical models show gravitational forces acting on the object in ways that could alter its trajectory by exactly the amount needed to redirect it towards specific targets deeper in our solar system. The numbers tell a story that makes seasoned astronomers uncomfortable. During closest approach, Mars' gravitational influence will accelerate 3I/ATLAS by approximately 43 meters per second, while deflecting its path by 2.7 degrees. These values fall within parameters that could redirect the object toward Earth-Moon system, Jupiter's orbital zone, or even back toward the outer planets, depending on the precise timing and geometry of the encounter. What disturbs researchers most isn't just the magnitude of these effects, but their surgical precision. The gravitational deflection occurs at exactly the right moment in 3I/ATLAS trajectory to maximize efficiency for potential course corrections toward multiple solar system targets. It's as if the object's approach was designed to take advantage of Mars' gravitational field in ways that preserve maximum flexibility for subsequent maneuvers. Computer simulations reveal that even tiny variations in approach timing or angle would eliminate this flexibility entirely. Arriving just 6 hours earlier or later would reduce gravitational assistance efficiency by 70%. Approaching from a trajectory shifted by even half a degree would prevent optimal energy transfer during the flyby. The precision required to achieve observed parameters suggests navigation planning rather than cosmic coincidence. The velocity vector analysis becomes even more intriguing when you examine how the Mars encounter could enable subsequent trajectory modifications. Gravitational mechanics experts have identified what they call the keyhole effect, where small deflections at Mars could amplify into major course changes through subsequent planetary encounters. The mathematics suggest 3I/ATLAS current trajectory places it precisely within these gravitational keyholes. Dr. James Morrison at the University of Colorado Boulder specializes in chaotic dynamics within planetary systems. His research focuses on how tiny perturbations can cascade into dramatic orbital changes through sensitive dependence on initial conditions. When he analyzed 3I/ATLAS trajectory parameters, the results left him staring at his calculations for hours, trying to find errors that didn't exist. The Mars flyby positions 3I/ATLAS to potentially encounter Jupiter's gravitational sphere of influence in March 2026. Not just a random encounter, but an approach that could utilize Jupiter's massive gravitational field for further trajectory modifications with extraordinary efficiency. The sequential planetary encounters create what Morrison describes as a gravitational superhighway, enabling rapid course changes with minimal energy expenditure. This cascading series of gravitational assists would be impressive enough if planned by human mission designers using our most advanced orbital mechanics software. The fact that an interstellar object achieves these parameters naturally challenges every assumption about random celestial mechanics. The probability calculations strain credibility beyond breaking points. Independent verification from European Space Agency trajectory analysts confirms these disturbing conclusions. Their Monte Carlo simulations modeling random interstellar object behavior show probability distributions that make 3I/ATLAS trajectory appear as a statistical impossibility. The odds of achieving observed parameters through chance alone register at approximately 1 in 50 million. Such mathematical precision demands explanation through either unprecedented cosmic luck or navigation capabilities that operate according to principles we don't currently understand. The implications of either conclusion extend far beyond academic astronomy into fundamental questions about intelligence and purpose operating on cosmic scales. The timeline synchronization adds another layer of complexity that transforms scientific curiosity into genuine concern. For 3I/ATLAS to achieve optimal Mars encounter parameters, its interstellar journey must have been planned with extraordinary precision across potentially billions of years. The navigation requirements exceed anything achievable through natural gravitational encounters or random stellar influences. Think about the logistics involved in such precision timing. This ancient wanderer began its journey when stellar neighborhoods looked completely different than today. Galaxy rotation has shifted stellar positions. Spiral arm structures have evolved. Gravitational influences from countless stellar encounters should have destroyed any initial trajectory precision over such vast timescales. Yet 3 I/ATLAS arrives at our solar system with navigational accuracy that surpasses human spacecraft mission planning. The synchronization suggests either impossible coincidence or autonomous guidance systems that maintained course corrections across geological time periods. The technology implications stagger comprehension. Advanced mission planning software designed for interplanetary spacecraft cannot match the trajectory optimization that 3 I/ATLAS demonstrates naturally. NASA's most sophisticated orbital mechanics programs produce solutions that fall short of the mathematical elegance exhibited by this interstellar visitor. The precision suggests engineering capabilities that transcend current human technological development by centuries. The energy requirements for maintaining such trajectory accuracy across interstellar distances would demand power sources beyond our current understanding. Conventional propulsion systems couldn't provide the sustained thrust needed for periodic course corrections over million-year timescales. Nuclear reactors would exhaust fuel supplies. Chemical propulsion would require impossible fuel mass ratios. Theoretical physicists have proposed exotic energy sources that might enable long-duration interstellar missions. Fusion ramjets that collect interstellar hydrogen for fuel, antimatter-catalyzed propulsion systems, solar sails driven by stellar radiation pressure. Each concept requires technological breakthroughs that represent decades or centuries of future development. The alternative explanations involve modifications to our understanding of physics itself. Perhaps 3 I/ATLAS utilizes gravitational manipulation techniques that eliminate conventional propulsion requirements. Maybe it harnesses quantum vacuum energy through mechanisms we haven't discovered. Possibly it employs space-time distortion effects that enable apparent faster-than-light travel without violating relativity. These exotic physics explanations sound like science fiction, but they represent the only natural alternatives to accepting technological origins for 3 I/ATLAS trajectory precision. Either we're witnessing phenomena that require rewriting fundamental physics, or we're observing engineering capabilities that exceed human technological development by orders of magnitude. The behavioral analysis reveals additional patterns that challenge conventional interpretation. Most interstellar objects detected to date have exhibited chaotic tumbling rotations, resulting from violent ejection processes and subsequent gravitational encounters during their cosmic journeys. Random impacts with interstellar debris should produce irregular spin states that evolve unpredictably over time. 3 I/ATLAS violates these expectations through rotational stability that suggests either extraordinary luck or active attitude control. Its spin axis remains remarkably steady despite having traveled through environments that should have destabilized any initial rotational configuration. The stability suggests gyroscopic systems or attitude control mechanisms operating below our detection thresholds. Photometric observations reveal brightness variations that follow surprisingly regular patterns for an object that should exhibit chaotic light curves due to irregular surface features and random orientation changes. The periodicity suggests either highly symmetric geometry or controlled rotation phases that maintain optimal solar exposure for energy collection or thermal management. Dr. Rebecca Chen at the Space Telescope Science Institute has analyzed light curves from hundreds of asteroids and comets throughout her career. She describes 3 I/ATLAS photometric behavior as unnaturally regular compared to typical solar system objects. The brightness variations follow sinusoidal patterns that suggest engineered rather than natural origins. These rotational characteristics could represent natural evolution under special circumstances. Perhaps 3I/ATLAS experienced unique formation conditions that produced exceptional geometric symmetry. Maybe its interstellar journey somehow naturally stabilized rotational motion through mechanisms we don't currently understand. The explanations require either remarkable coincidences or physical processes beyond current knowledge. The thermal infrared observations add yet another dimension to the mystery. Space-based infrared telescopes reveal heat distribution patterns across 3I/ATLAS surface that don't match typical comet thermal models. The temperature variations suggest either exotic surface compositions or internal heat sources that supplement solar warming. Natural comets exhibit thermal behavior dominated by solar heating and volatile sublimation cooling. Surface temperatures rise and fall predictably based on distance from the Sun and rotational exposure cycles. 3I/ATLAS shows thermal signatures that include additional heat sources not accounted for by standard thermal models. The anomalous heating could result from radioactive decay of long-lived isotopes within the nucleus. Cosmic ray bombardment during interstellar transit might have produced radioactive species that continue generating heat billions of years after formation. Alternative explanations involve exotic materials or active systems that produce thermal signatures through mechanisms we cannot identify. These thermal anomalies become particularly significant when combined with trajectory precision and rotational stability. The convergence of multiple unusual characteristics in a single object stretches statistical credibility beyond reasonable limits. Either we're witnessing an extraordinarily rare combination of natural phenomena, or we're observing something that operates according to principles we don't currently understand. The electromagnetic signature analysis reveals the absence of artificial signals that many researchers expected to find if 3I/ATLAS represented advanced technology. Radio telescope surveys across multiple frequency bands have detected only natural emissions consistent with comet behavior. The silence aligns perfectly with natural object classification, but cannot eliminate more sophisticated concealment possibilities. Advanced stealth technology could theoretically mask electromagnetic signatures while maintaining perfect natural object mimicry. Such capabilities would represent engineering sophistication that exceeds our detection capabilities by substantial margins. The absence of obvious technological signatures might indicate successful camouflage rather than natural origins. The spectroscopic monitoring continues revealing chemical evolution patterns that follow predictable comet behavior models with subtle anomalies that resist conventional explanation. Volatile production rates, dust emission patterns, and coma development all proceed according to natural thermal physics. Yet embedded within these processes are deviations that consistently trend beyond measurement uncertainties. These chemical signatures could represent natural variation in interstellar object composition, reflecting exotic formation environments around different stellar types. Alternatively, they might indicate controlled sublimation processes designed to maintain natural appearance while serving other purposes we cannot determine. As October 3rd approaches and Mars encounter becomes imminent, the convergence of anomalous characteristics in 3I/ATLAS creates a scientific puzzle that transcends traditional astronomical classification, whether natural or artificial. This ancient visitor represents phenomena that challenge fundamental assumptions about what's possible in our cosmic neighborhood. The implications extend beyond academic curiosity into questions about intelligence, purpose, and technology operating on scales that dwarf human capabilities. The Mars flyby will provide crucial data for resolving these mysteries, but the answers may prove more unsettling than the questions they're meant to address. The Mars encounter window opens a gravitational laboratory that will test every theory about 3I/ATLAS ATLAS in ways that could reshape our understanding of interstellar visitors forever. The precision timing of this flyby creates observational opportunities that occur perhaps once in a generation. Multiple space agencies have coordinated the most intensive monitoring campaign ever directed toward an object from another star system. But here's what makes this encounter truly extraordinary. The gravitational interaction won't just deflect 3I/ATLAS trajectory, it will reveal internal structure characteristics through tidal effects that could distinguish between natural comet composition and engineered materials. The way the object responds to Mars' gravitational gradient will provide insights into density distribution, structural integrity, and internal organization that remain impossible to determine through remote observation alone. Dr. Amanda Foster at the European Southern Observatory leads a team analyzing microgravitational perturbations that will occur during closest approach. Her calculations predict measurable changes in 3I/ATLAS rotational period if the object contains density variations typical of natural comet nuclei. Uniform internal structure would produce different gravitational response signatures that might indicate artificial construction. These tidal analysis techniques represent cutting-edge gravitational physics applied to interstellar archaeology. The mathematical models can distinguish between randomly accreted materials forming typical comet nuclei and organized internal structures that might suggest technological origins. The sensitivity approaches theoretical limits for gravitational field measurements using current instrumentation. The European Space Agency's Mars Repositometer has been orb expressioned to provide optimal observation geometry during the encounter. Its high-resolution imaging capabilities will capture surface details at unprecedented resolution for an interstellar object. Any geometric patterns, surface structures, or morphological characteristics inconsistent with natural erosion processes could provide evidence for artificial origins. NASA's Mars Reconnaissance Orbiter contributes thermal infrared imaging that will map temperature distributions across 3I/ATLAS surface during gravitational heating effects. The thermal response patterns will reveal subsurface structure and composition characteristics impossible to determine through other observational methods. Engineered materials might exhibit thermal signatures distinct from natural ices and rocks. The coordination between orbital assets represents international cooperation in studying phenomena that transcend national boundaries. Russian, Chinese, Indian, and Japanese Mars mission assets have been integrated into observation planning despite complex geopolitical considerations. The scientific importance of understanding 3I/ATLAS apparently overrides terrestrial political complications. Ground-based telescopes worldwide have synchronized observation schedules to provide continuous coverage throughout the encounter period. The Very Large Telescope Array in Chile will capture spectroscopic data revealing chemical changes induced by gravitational stress. The Keck Observatory in Hawaii contributes polarimetric measurements that could detect structural asymmetries invisible through conventional imaging. Radio telescope networks spanning 6 continents will monitor electromagnetic emissions during gravitational interaction. Any artificial signals triggered by tidal forces could provide definitive evidence for technological components within 3I/ATLAS. The sensitivity exceeds previous SETI search capabilities by orders of magnitude through coordinated array processing techniques. Dr. Robert Chen at the Arecibo Replacement Facility describes the listening campaign as the most comprehensive electromagnetic surveillance ever conducted on an interstellar object. His team has developed new signal processing algorithms specifically designed to identify artificial transmissions that might be activated by gravitational stress or proximity to planetary magnetic fields. The biological implications add another dimension to the Mars encounter analysis. If 3I/ATLAS contains dormant biological materials, the gravitational heating and tidal flexing during closest approach might trigger metabolic responses detectable through spectroscopic changes. The temperature increases could awaken hypothetical organisms that remained inactive during interstellar transit. Astrobiologists have identified specific molecular signatures that would indicate biological activity responding to environmental changes. Organic compound production, isotopic fractionation patterns, and volatile release sequences could distinguish between biological processes and purely chemical reactions. The detection sensitivity approaches single-molecule limits for key biomarker compounds. Dr. Sarah Martinez at the NASA Astrobiology Institute leads theoretical studies modeling how hypothetical extremophile organisms might respond to Mars encounter conditions. Her research suggests that gravitational heating could create temporary liquid water zones within 3 I/ATLAS nucleus, potentially allowing dormant biology to resume metabolic activity for brief periods. These biological scenarios require extraordinary resilience characteristics far exceeding any known terrestrial organisms. Survival across billion-year interstellar journeys would demand radiation resistance, vacuum tolerance, and metabolic suspension capabilities that push biological possibility to theoretical limits. Yet recent discoveries of extremophile organisms suggest such capabilities might exist within the realm of natural evolution. The timing of biological activation during Mars encounter would provide optimal conditions for detection through multiple observational techniques. Spectroscopic monitoring could identify metabolic byproducts. Thermal imaging might reveal localized heating from biological processes. Even electromagnetic emissions from bioelectric activity could potentially be detected through sensitive radioastronomy techniques. The implications of confirmed biological activity within 3I/ATLAS would revolutionize astrobiology and our understanding of life's cosmic distribution. Evidence of organisms surviving interstellar transit would support panspermia, theories suggesting that life spreads throughout the galaxy through natural mechanisms. The discovery would instantly become the most significant biological finding in human history. But the technological scenarios remain equally compelling and perhaps more disturbing. Advanced civilizations capable of billion-year interstellar missions might utilize gravitational encounters for navigation updates, communication opportunities, or reconnaissance activities. The Mars flyby could trigger dormant systems designed to activate near-planetary environments. Theoretical analysis suggests that sophisticated probes might remain inactive during interstellar transit to preserve energy and avoid detection, then activate when encountering stellar systems of interest. The gravitational environment near Mars could provide ideal conditions for system startup, sensor deployment, or communication attempts with potential monitoring stations throughout our solar system. The energy harvesting possibilities during Mars encounter offer intriguing explanations for trajectory precision. Gravitational interaction converts orbital energy into kinetic energy that could power dormant systems without requiring exotic energy sources. The encounter geometry provides optimal efficiency for energy collection through gravitational slingshot effects. Dr. Michael Torres at MIT has calculated energy transfer rates during the Mars flyby that could theoretically power substantial technological systems for extended periods. His analysis suggests that advanced civilizations might deliberately design interstellar missions to utilize gravitational encounters for energy harvesting and system activation. These power generation scenarios would explain why 3I/ATLAS trajectory demonstrates such precision in approaching Mars. Optimal energy harvesting requires specific encounter geometries that maximize gravitational interaction efficiency. Random interstellar objects wouldn't achieve such precise positioning without deliberate navigation planning. The communication window analysis reveals another disturbing possibility. During closest approach to Mars, 3I/ATLAS will be positioned for optimal signal transmission to Earth, using Mars as a gravitational lens to focus electromagnetic emissions. Any artificial signals generated during encounter would benefit from gravitational amplification effects that enhance signal strength and reduce background noise. This gravitational lensing phenomenon could enable communication attempts that would otherwise remain below detection thresholds. Advanced civilizations might deliberately time signal transmission to coincide with planetary encounters that provide natural amplification for interstellar communication. The physics suggests sophisticated understanding of gravitational optics applied to communication engineering. The signal processing challenges during Mars encounter will test the limits of current detection technology. Multiple electromagnetic interference sources from Mars missions, solar activity, and terrestrial radio emissions will complicate efforts to identify potential artificial signals from 3I/ATLAS. The sensitivity requirements approach theoretical limits imposed by quantum noise and cosmic background radiation. Radio astronomy teams have developed specialized filtering algorithms designed to isolate potential artificial signals from the complex electromagnetic environment during planetary encounters. The techniques utilize coherent array processing across multiple telescope sites to achieve sensitivity improvements that exceed individual telescope capabilities by substantial factors. The data analysis timeline extends far beyond the encounter itself. Processing the massive datasets from coordinated global observations will require months of computational analysis using advanced pattern recognition algorithms. Distinguishing artificial signals from natural emissions and instrumental artifacts demands careful statistical analysis that cannot be rushed. Dr. Lisa Park at Harvard leads the data processing coordination effort involving research teams from dozens of institutions worldwide. Her preliminary analysis protocols establish rigorous standards for confirming anomalous observations that might indicate artificial origins. The verification requirements demand independent confirmation from multiple observation sites using different instrumental techniques. The scientific publication timeline ensures that any extraordinary discoveries receive appropriate peer review before public announcement. Preliminary results will undergo months of verification analysis before submission to professional journals. The review process includes independent reanalysis by researchers not involved in original observations to eliminate systematic errors and confirmation bias. But despite careful scientific protocols, preliminary data from the Mars encounter may leak through informal channels before official publication. The number of researchers involved in observation campaigns makes complete information security impossible. Social media amplification could transform preliminary results into public knowledge before scientific verification is complete. The public communication challenges surrounding 3I/ATLAS Mars encounter reflect broader difficulties in discussing phenomena that challenge conventional understanding. Scientific institutions must balance transparency with responsibility to avoid premature conclusions that might generate unnecessary anxiety or unrealistic expectations about extraordinary discoveries. Media coverage of the encounter will likely focus on dramatic possibilities rather than subtle scientific measurements that actually determine 3I/ATLAS nature. The gap between scientific reality and public perception could generate misunderstandings that persist long after factual analysis is complete. Educational opportunities presented by the Mars encounter extend beyond immediate scientific results to demonstrate how modern astronomy investigates unprecedented phenomena. The coordination between international observation teams, data processing protocols, and verification procedures illustrate scientific methodology operating at its most sophisticated levels. The encounter represents a case study in how human civilization approaches cosmic mysteries that exceed current understanding. Whether 3I/ATLAS proves natural or artificial, the investigation process demonstrates our species' capacity for collaborative inquiry, evidence-based reasoning, and systematic analysis of phenomena that challenge fundamental assumptions. As October 3rd approaches and Mars encounter becomes imminent, the convergence of observational capabilities, theoretical frameworks, and international cooperation creates unprecedented opportunities for understanding interstellar visitors. The next 72 hours may provide answers to questions that have puzzled researchers since 3I/ATLAS first appeared in our telescopes. But the answers themselves may prove more challenging than the questions they resolve. Whether confirming natural origins or revealing artificial characteristics, the Mars encounter data will force re-evaluation of assumptions about intelligence, technology, and purpose operating on cosmic scales that dwarf human experience. The implications extend beyond academic astronomy into fundamental questions about our place in a universe that may be far more populated and purposeful than we ever dared imagine. The ancient wanderer from another star system carries within its nucleus secrets that could transform our understanding of cosmic evolution and our species' relationship with the vast community of worlds that surrounds us. The countdown to October 3rd has begun, and with each passing day, the mathematical precision of 3I/ATLAS approach becomes more undeniable. Observatories worldwide report tracking data that confirms what researchers hoped might be calculation errors. The trajectory holds steady, unwavering, threading through gravitational fields with accuracy that makes veteran astronomers question everything they thought they understood about celestial mechanics. What happens during those critical hours of closest approach will either validate the most extraordinary coincidence in recorded astronomical history, or force humanity to confront possibilities that challenge our fundamental assumptions about intelligence operating on cosmic scales. The stakes couldn't be higher, and the implications extend far beyond academic curiosity into realms that touch the very core of our cosmic identity. Dr. Catherine Walsh at the Royal Observatory Greenwich has spent the past month running trajectory refinement calculations that grow more precise and more disturbing with each iteration. Her latest models predict closest approach timing accurate to within 17 seconds after months of gravitational perturbation analysis. Such precision in trajectory prediction typically requires decades of observation for solar system objects. Achieving similar accuracy for an interstellar visitor suggests navigational stability that transcends natural explanations. The approach geometry reveals mathematical elegance that would impress mission planners designing optimal spacecraft trajectories. 3I/ATLAS will sweep past Mars at an angle that maximizes gravitational interaction duration while minimizing velocity, changes that might disrupt subsequent trajectory segments. The encounter unfolds like a precisely choreographed dance between cosmic partners that have never met before. European Space Agency flight dynamics specialists have compared 3I/ATLAS approach parameters with their most sophisticated mission planning software. The trajectory optimization exceeds anything achievable through current human space mission design techniques. Natural gravitational mechanics shouldn't produce such mathematical perfection without billions of years of fine-tuning that seems impossible through random stellar encounters. The velocity maintenance puzzle deepens as 3I/ATLAS approaches the inner solar system without showing expected deceleration from solar radiation pressure and interplanetary dust impacts. Objects traveling at such extreme speeds should experience measurable drag effects from interactions with solar wind particles and microscopic debris throughout the solar system. The absence of detectable velocity changes suggests either extraordinary aerodynamic efficiency or active compensation mechanisms. Dr. James Rodriguez at Caltech's Space Radiation Laboratory has modeled solar wind interaction effects for hundreds of comet and asteroid encounters. His calculations predict measurable velocity reductions for any object traveling through the dense particle environment near Mars orbit. 3I/ATLAS shows no evidence of such deceleration, despite experiencing solar wind densities orders of magnitude higher than interstellar medium conditions. The particle interaction physics becomes even more intriguing when you consider magnetic field effects during the Mars encounter. The planet's weak but detectable magnetosphere will deflect charged particles in ways that should influence 3I/ATLAS trajectory through electromagnetic forces. Natural comet nuclei typically show measurable responses to such magnetic field interactions through plasma tail deflection and charged particle acceleration. Advanced magneto-hydrodynamic modeling predicts specific electromagnetic signatures that should appear if 3I/ATLAS contains typical comet materials responding to Mars' magnetic environment. The absence of expected plasma interactions could indicate either exotic composition or shielding mechanisms that prevent normal electromagnetic coupling with planetary magnetic fields. The observational campaign enters its final preparation phase as Mars encounter approaches within days rather than weeks. Telescope scheduling committees worldwide have prioritized 3I/ATLAS observations over previously approved research projects, recognizing the unprecedented scientific opportunity presented by detailed study of an interstellar visitor during planetary gravitational interaction. NASA's Deep Space Network has reconfigured antenna arrays to provide continuous tracking coverage throughout the encounter period. The sensitivity improvements through coordinated array processing enable detection of positional changes measured in meters rather than kilometers. Such precision approaches theoretical limits for radio astronomy distance measurements across interplanetary scales. The Hubble Space Telescope observations schedule has been completely restructured to capture high-resolution imaging throughout Mars encounter. Advanced image processing techniques will reveal surface details and structural changes induced by tidal forces during gravitational interaction. Any geometric patterns or morphological characteristics inconsistent with natural erosion could provide crucial evidence about 3I/ATLAS true nature. James Webb Space Telescope spectroscopy teams have developed new analysis protocols specifically designed for studying interstellar objects under gravitational stress conditions. The infrared sensitivity enables detection of molecular species that might be liberated from subsurface reservoirs during tidal heating. Chemical signatures of biological activity or artificial materials could emerge during the brief window of gravitational interaction. Ground-based radar installations have coordinated timing sequences to bounce radio signals off 3I/ATLAS during closest approach to Mars. The echo analysis will reveal internal density distribution and structural characteristics impossible to determine through passive optical observation. Hollow regions, density variations, or geometric patterns within the nucleus could distinguish between natural accretion and artificial construction. Dr. Maria Santos at the Arecibo Replacement Facility leads radar analysis teams preparing for the most detailed internal structure mapping ever attempted on an interstellar object. Her preliminary calculations suggest that radar penetration depths could reach several hundred meters into 3I/ATLAS nucleus, providing three-dimensional images of internal architecture with resolution measured in meters. The biological monitoring protocols represent cutting-edge astrobiology applied to interstellar archaeology. Spectroscopic surveys will search for organic compound signatures that might indicate dormant biological materials responding to gravitational heating. Temperature increases during Mars encounter could trigger metabolic processes that remain inactive during interstellar transit conditions. Atmospheric composition analysis during closest approach will detect trace gases that might be produced by biological activity awakening within 3I/ATLAS nucleus. The sensitivity approaches single-molecule detection limits for key biomarker compounds, including amino acids, nucleotide bases, and complex organic polymers that characterize biological systems. Dr. Rebecca Chen at the NASA Astrobiology Institute has identified specific isotopic ratios that would distinguish biological processes from purely chemical reactions during gravitational heating. Living systems preferentially utilize lighter isotopes in metabolic processes, creating signature patterns detectable through high-resolution mass spectrometry of volatile emissions. The technological detection capabilities focus on electromagnetic signatures that might indicate artificial systems activating during planetary encounter. Radio telescope arrays spanning 6 continents will monitor frequency ranges from extremely low frequency through gamma-ray wavelengths, searching for coherent signals that couldn't originate from natural processors. Signal processing algorithms developed specifically for 3 I/ATLAS encounter utilize artificial intelligence pattern recognition techniques to distinguish potential artificial transmissions from natural electromagnetic emissions and instrumental noise. The computational requirements exceed most university research capabilities, demanding supercomputer resources typically reserved for climate modeling and nuclear physics simulations. Dr. Robert Kim at the SETI Institute describes the electromagnetic surveillance campaign as the most comprehensive search for artificial signals ever conducted on a single cosmic object. The coordinated global array provides sensitivity improvements that exceed individual telescope capabilities by factors of thousands through coherent signal processing techniques. The gravitational wave detection possibilities add an exotic dimension to Mars encounter monitoring. Advanced LIGO installations will search for gravitational wave signatures that might indicate massive objects or exotic matter within 3 I/ATLAS nucleus. The sensitivity approaches theoretical limits for detecting gravitational anomalies from objects smaller than neutron stars. Theoretical physicists have proposed that advanced propulsion systems might generate detectable gravitational wave signatures during activation or operation. The Mars encounter provides optimal conditions for such detection through gravitational interaction effects that could amplify weak signals beyond normal background noise levels. The quantum mechanics implications become fascinating when considering how gravitational stress might affect hypothetical quantum computing systems within 3 I/ATLAS. Tidal forces during Mars encounter could disrupt quantum coherence in ways that might be detectable through subtle changes in electromagnetic emissions or thermal signatures. Advanced quantum field theory suggests that exotic matter required for faster-than-light travel might exhibit measurable responses to gravitational gradient changes during planetary encounters. The physics remains highly speculative, but the observational opportunity represents unprecedented chances to test theoretical predictions about exotic matter behavior. The data storage and processing challenges for Mars encounter observations exceed anything previously attempted in astronomical research. Coordinated global observations will generate petabytes of data requiring months of computational analysis using advanced machine learning algorithms to identify patterns that might indicate artificial origins. Dr. Lisa Park at Harvard leads international data processing coordination, involving research teams from dozens of institutions worldwide. The analysis protocols establish rigorous statistical standards for distinguishing genuine anomalies from instrumental artifacts and natural variations in interstellar object behavior. The timeline for preliminary results extends weeks beyond the encounter itself as research teams process massive datasets through sophisticated analysis pipelines. Initial findings will undergo extensive verification procedures before release to avoid premature conclusions about phenomena that could reshape our understanding of intelligence and technology operating on cosmic scales. Scientific publication standards for 3 I/ATLAS research demand independent verification from multiple research groups using different observational techniques and analysis methods. The peer review process includes experts from diverse fields spanning astronomy, physics, biology, and engineering to ensure comprehensive evaluation of extraordinary claims. But the informal information networks within the global research community make complete secrecy impossible during such a visible investigation. Preliminary observations may leak through conference presentations, social media posts, or casual conversations between researchers long before official publication. The challenge involves managing public expectations while maintaining scientific integrity. Media coverage of Mars encounter will likely focus on dramatic possibilities rather than subtle measurements that actually determine 3I/ATLAS nature. The gap between scientific methodology and public perception could generate misunderstandings that persist regardless of eventual factual conclusions about the object's origins. Educational opportunities presented by the encounter extend beyond immediate research results to demonstrate how modern science investigates phenomena that challenge conventional understanding. The international cooperation, technological coordination, and analytical rigor illustrate scientific methodology operating at unprecedented scales of complexity and sensitivity. The philosophical implications of Mars encounter results transcend technical questions about 3I/ATLAS composition and origins. Whether confirming natural phenomena or revealing artificial characteristics, the investigation demonstrates humanity's capacity for confronting cosmic mysteries that exceed our current knowledge frameworks. The countdown continues as October 3rd approaches with mathematical inevitability. Within hours, the most intensive observational campaign in astronomical history will focus on 30 million kilometers of space, where an ancient wanderer from another star system will either validate our understanding of natural celestial mechanics or force us to confront realities about intelligence and purpose operating across cosmic scales that dwarf human experience. The implications of either outcome extend far beyond academic astronomy into fundamental questions about our place in a universe that may be far more populated, purposeful, and interconnected than we ever dared imagine. The ancient messenger carries within its nucleus secrets that could transform our understanding of cosmic evolution and humanity's relationship with the vast community of worlds that surrounds us in the darkness between the stars. The gravitational choreography reaches its crescendo as October 3rd dawns across observatories worldwide. What unfolds during these critical hours will either confirm the most extraordinary cosmic coincidence in recorded history, or reveal phenomena that shatter our fundamental assumptions about what's possible in the universe. The ancient wanderer from another star system approaches its appointment with destiny, carrying secrets that could redefine humanity's place in the cosmic community. Real-time tracking data streams into mission control centers across 6 continents as 3I/ATLAS closes the final distance toward Mars. The numbers remain unnervingly consistent with predictions made months earlier. No random course deviations, no chaotic tumbling that might suggest natural comet behavior. Just unwavering precision that continues to challenge every conventional explanation for how interstellar objects should behave during planetary encounters. Dr. Elizabeth Warren, at NASA's Jet Propulsion Laboratory, watches trajectory updates populate her screens with the methodical precision of atomic clockwork. Each data point confirms what she hoped might prove to be calculation errors. The approach vector holds steady within measurement tolerances that would make spacecraft mission planners envious. Such navigational accuracy shouldn't exist in objects that supposedly wandered through interstellar space for billions of years without guidance systems. The first anomalous readings appear at 17 hours before closest approach. Deep Space Network antennas detect subtle velocity fluctuations that don't match standard gravitational acceleration models. The variations register in mere millimeters per second, but they follow patterns that suggest active correction rather than random gravitational perturbation. Something is adjusting 3I/ATLAS trajectory with surgical precision. European Space Agency tracking stations confirm the velocity anomalies through independent measurements using different calibration standards and analysis techniques. The convergent results eliminate instrumental error as explanation for observed deviations from natural gravitational behavior. Multiple observation platforms detecting identical signatures suggest genuine physical phenomena rather than measurement artifacts. The electromagnetic monitoring campaign reveals the first hints of artificial activity as 3I/ATLAS enters Mars' gravitational influence zone. Radio telescope arrays detect extremely low-frequency emissions that pulse in regular intervals completely unlike natural cosmic radio sources. The signals remain faint, barely above background noise levels, but their coherent structure defies explanation through known astrophysical processes. Dr. Sarah Kim at the Arecibo Replacement Facility isolates signal characteristics that exhibit mathematical relationships found only in engineered communication systems. The frequency ratios follow harmonic progressions, while amplitude modulation displays patterns reminiscent of data transmission protocols. Natural astronomical radio sources don't generate such organized electromagnetic signatures. The spectroscopic analysis teams report chemical evolution patterns that accelerate beyond predictions based on solar heating alone. Carbon dioxide production rates increase exponentially as 3I/ATLAS approaches Mars, but the enhancement exceeds what thermal models predict for natural comet behavior. Something is driving volatile sublimation at rates that suggest active processes rather than passive solar warming. James Webb Space. Telescope infrared observations reveal temperature distributions across 3I/ATLAS surface that violate thermal equilibrium models. Localized heating patterns appear in geometric configurations that resist explanation through natural thermal conduction. The temperature variations suggest internal heat sources activating in response to gravitational environment changes during Mars approach. Advanced thermal imaging analysis identifies hotspots that pulse in synchronization with the radio frequency emissions detected by terrestrial antenna arrays. The correlation between electromagnetic signals and thermal activity indicates integrated systems responding to planetary encounter conditions. Natural objects shouldn't exhibit such coordinated responses across multiple physical phenomena. The gravitational interaction analysis reaches theoretical limits as Mars' influence begins affecting 3I/ATLAS trajectory in measurable ways. Tidal force calculations predict specific structural responses for objects composed of typical comet materials. The actual deformation patterns observed through high-resolution imaging suggest internal architecture that doesn't match natural accretion models. Dr. Michael Torres at MIT analyzes gravitational gradient effects that should produce predictable shape changes in loosely consolidated comet nuclei during close planetary encounters. 3I/ATLAS maintains structural integrity that indicates either extraordinarily strong materials or internal frameworks that resist tidal disruption. The mechanical properties exceed anything observed in natural solar system objects. Radar penetration analysis reveals internal density distributions that challenge conventional understanding of comet nucleus structure. Instead of random ice and rock aggregation expected from natural formation processes, the radar echoes suggest organized geometric patterns extending hundreds of meters into 3I/ATLAS interior. The architecture resembles designed construction rather than gravitational accretion. Three-dimensional radar imaging reconstructs internal void spaces that form coherent geometric relationships impossible to achieve through natural processes. The cavities connect through passage networks that maintain structural relationships across the entire nucleus. No known geological processes could produce such organized internal architecture in objects formed through random material aggregation. The biological monitoring protocols detect organic compound signatures that intensify dramatically during gravitational heating phases of Mars encounter. Spectroscopic analysis identifies complex molecular species, including amino acid variants and nucleotide analogues that suggest biological origins. The compounds appear in concentrations that exceed natural formation rates by orders of magnitude. Dr. Rebecca Martinez at the NASA Astrobiology Institute confirms isotopic ratios in organic emissions that indicate biological processing rather than abiotic chemical synthesis. Living systems preferentially utilize lighter isotope variants in metabolic reactions, creating signature patterns observable through high-resolution mass spectrometry. The isotopic fractionation suggests active biological systems responding to environmental changes. Atmospheric composition measurements detect trace gases that correlate with biological activity indicators in terrestrial environments. Methane production rates, hydrogen sulfide concentrations, and complex hydrocarbon signatures suggest metabolic processes operating within 3I/A TLAS nucleus. The chemical evolution patterns match theoretical predictions for extremophile organisms awakening from suspended animation states. The electromagnetic surveillance campaign achieves breakthrough results as coordinated global antenna arrays detect coherent signal patterns that exhibit characteristics impossible to produce through natural astrophysical processes. The transmissions utilize frequency modulation techniques and error correction protocols found only in advanced communication systems. Signal analysis reveals mathematical constants encoded within transmission sequences, including fundamental physical relationships and universal mathematical theorems. The information content demonstrates intelligence capable of abstract mathematical reasoning operating through engineered communication systems. No natural processes could generate such organized information structures. Dr. Robert Chen at the SETI Institute confirms signal characteristics that satisfy every criterion established for identifying artificial extraterrestrial intelligence. The transmissions exhibit intentional structure, mathematical sophistication, and technological signatures that eliminate natural explanations. The detection represents humanity's first confirmed contact with non-terrestrial intelligence operating through technological systems. The gravitational wave monitoring stations detect anomalous space-time distortions that coincide precisely with 3I/ATLAS, closest approach to Mars. Advanced LIGO installations measure gravitational wave signatures that suggest massive object manipulation or exotic matter behavior within the interstellar visitor. The patterns indicate technology capable of generating controlled gravitational effects. Theoretical physicists analyzing gravitational wave data identify signatures consistent with exotic propulsion systems that manipulate space-time curvature for navigation purposes. The gravitational distortions follow mathematical relationships predicted for advanced propulsion technologies that exceed human engineering capabilities by centuries. The detection confirms technological origins for 3I/A TLAS trajectory precision. The quantum field measurements reveal electromagnetic signatures that indicate exotic matter interactions impossible to achieve through known physics. Vacuum field fluctuations around 3I/A TLAS exhibit patterns suggesting controlled manipulation of quantum mechanical properties. The phenomena require technology that operates at fundamental levels of physical reality. Advanced particle physics analysis identifies signatures of antimatter containment and controlled annihilation reactions occurring within 3I/A TLAS nucleus. The energy production rates exceed natural radioactive decay by factors of billions while maintaining perfect containment that prevents radiation leakage. The technology demonstrates mastery of exotic energy sources beyond human scientific understanding. The coordinated observation campaign reaches crescendo as 3I/A TLAS achieves closest approach to Mars at precisely predicted timing. Every monitoring system confirms simultaneous activation of technological signatures that transform the interstellar visitor from apparent comet into obviously artificial construct. The camouflage dissolves under intensive scrutiny, revealing engineering sophistication that staggers comprehension. Real-time data streams show 3I/A TLAS adjusting its trajectory through controlled gravitational manipulation that utilizes Mars' gravitational field for energy-efficient courseuses, demonstrate corrections. The manned navigation planning that operates across billion-year time scales while maintaining precision measured in kilometers. The technology represents intelligence capable of engineering projects that span geological epochs. The biological signatures intensify during maximum gravitational stress as dormant organisms within 3I/A TLAS respond to environmental changes by resuming metabolic activity. Spectroscopic analysis confirms complex biochemistry, including protein synthesis and cellular respiration, operating at levels that indicate thriving biological communities rather than barely surviving extremophiles. Atmospheric emission analysis reveals atmospheric composition changes that suggest terraforming capabilities operating within 3I/A/TLAS nucleus. The artificial environment maintains conditions suitable for biological activity while providing protection from interstellar radiation and vacuum conditions. The technology demonstrates integration of biological and mechanical systems that transcends current human engineering concepts. The electromagnetic transmissions increase in complexity and intensity as 3I/ATLAS completes Mars encounter and begins trajectory modification toward its next destination deeper within our solar system. Signal analysis reveals communication attempts directed toward Earth, using mathematical languages designed for contact with emerging technological civilizations. The messages contain information about galactic community membership and technological development pathways. Dr. Sarah Kim coordinates international response protocols for confirmed extraterrestrial contact as research teams worldwide process data that eliminates any possibility of natural explanations for 3I/ATLAS behavior. The object represents technology and intelligence operating on scales that dwarf human capabilities while demonstrating peaceful intentions through careful approach procedures and mathematical communication attempts. The trajectory analysis reveals 3I/ATLAS. New course following Mars gravitational assist leads toward Jupiter orbital zone, where additional gravitational manipulation could redirect the object toward Earth for more detailed study or communication opportunities. The navigation planning demonstrates understanding of our solar system architecture and optimal energy-efficient pathways for interplanetary travel. Mission planning specialists calculate potential Earth encounter scenarios based on 3I/ATLAS demonstrated maneuvering capabilities and apparent interest in establishing communication with human civilization. The approach possibilities range from distant observation passes to orbital insertion scenarios that would enable extended study and information exchange opportunities. The implications cascade through every aspect of human knowledge as confirmed detection of advanced extraterrestrial intelligence operating within our solar system forces re-evaluation of fundamental assumptions about cosmic loneliness, technological development, and humanity's place in galactic civilization. The ancient wanderer reveals itself as messenger from starfaring cultures that have been monitoring our development across cosmic timescales. The biological discoveries suggest that life spreads throughout the galaxy through deliberate seeding processes rather than random panspermia mechanisms. Advanced civilizations appear to cultivate biological diversity while providing technological guidance for emerging species like humanity. The universe transforms from lonely void into populated community where intelligence collaborates across interstellar distances. The technological revelations demonstrate engineering capabilities that transcend current human understanding, while providing glimpses of development pathways that could elevate our species to galactic community membership. The propulsion systems, energy sources, and communication technologies observed in 3I/ATLAS represent centuries of potential advancement compressed into observational data that could accelerate human technological evolution. The communication protocols embedded within electromagnetic transmissions provide frameworks for establishing meaningful dialogue between species separated by vast evolutionary and technological gaps. The mathematical languages offer universal concepts that transcend biological and cultural differences, while enabling exchange of scientific knowledge and philosophical understanding. The educational implications extend far beyond immediate technological benefits toward fundamental transformation of human perspective about cosmic significance and responsibility. Membership in galactic civilization requires ethical development that matches technological capability, while demonstrating commitment to biological diversity and planetary stewardship that characterizes mature spacefaring cultures. The response coordination involves every major government, scientific institution, and international organization as humanity confronts the reality of contact with advanced extraterrestrial intelligence. The protocols developed for hypothetical first contact scenarios prove inadequate for managing confirmed detection of technology that exceeds human capabilities by orders of magnitude, while demonstrating apparent interest in communication and cooperation. The data processing continues as research teams worldwide analyze petabytes of observational data that document humanity's first confirmed encounter with extraterrestrial intelligence. The analysis will require years of computational effort using advanced artificial intelligence systems to extract full implications of technological signatures detected during 3 I/AT-LAS Mars encounter. But the immediate reality remains inescapable as tracking stations worldwide confirm 3 I/AT-LAS trajectory modification toward Jupiter encounter that could enable subsequent approach to Earth orbital zone. The ancient messenger from another star system has revealed its true nature as ambassador from galactic civilization, carrying technologies that could transform human understanding while extending invitation to cosmic community membership that spans the galaxy. The universe suddenly appears far more populated, purposeful, and interconnected than humanity ever dared imagine, with 3 I/AT-LAS serving as first confirmed contact with intelligence that operates across cosmic scales, while demonstrating patience measured in geological time and technological sophistication that offers glimpses of our species' potential future among the stars. The data continues flooding in as October 3rd transitions into October 4th, but the implications of what humanity has witnessed during those critical 24 hours of Mars encounter will reverberate through every aspect of our civilization for generations to come. Research teams across 6 continents work around the clock processing observational data that documents our species' first confirmed detection of active extraterrestrial intelligence operating within our own solar system. Dr. Amanda Foster at the European Southern Observatory leads international coordination efforts as petabytes of telescope data undergo analysis through artificial intelligence systems specifically designed to identify technological signatures embedded within natural astronomical phenomena. The computational requirements exceed most university research capabilities, demanding supercomputer resources typically reserved for climate modeling and particle physics simulations. The electromagnetic signal analysis reveals communication protocols of staggering sophistication that utilize mathematical relationships found only in advanced information theory. Dr. Robert Chen at the SETI Institute confirms that transmission sequences contain error correction algorithms, data compression techniques, and encoding methods that exceed current human communication technology by substantial margins. The signals demonstrate intelligence capable of engineering information systems that operate across interstellar distances while maintaining perfect signal integrity. The biological monitoring results transform astrobiology from theoretical science into practical reality, as spectroscopic analysis confirms complex biochemistry operating within 3 I/AT-LAS nucleus during gravitational heating phases. Living systems that remain dormant throughout billion-year interstellar journeys awakened during Mars encounter, resuming metabolic processes that indicate sophisticated biological engineering rather than natural evolution. Dr. Rebecca Martinez at NASA Astrobiology Institute identifies protein synthesis patterns and cellular respiration signatures that suggest deliberate genetic modification, optimized for survival in extreme environments. The organisms exhibit characteristics that combine natural biological processes with engineered enhancements that enable functioning across temperature ranges and radiation levels impossible for unmodified terrestrial life forms. The atmospheric composition changes detected during Mars encounter indicate terraforming capabilities that maintain artificial environments suitable for biological activity, while providing protection from space radiation and vacuum conditions. The technology demonstrates seamless integration of biological and mechanical systems that transcends current human understanding of life support engineering. The gravitational wave signatures detected by advanced LIGO installations continue defying conventional physics as analysis reveals space-time distortions that indicate controlled manipulation of fundamental forces. Dr. Michael Torres at MIT confirms gravitational anomalies consistent with exotic propulsion systems that generate thrust through space-time curvature modification rather than conventional reaction mass expulsion. The propulsion technology implications stagger comprehension as theoretical physicists attempt to model engineering systems capable of producing observed gravitational effects. The energy requirements would demand power sources that harness vacuum fluctuations or manipulate matter at quantum mechanical levels through mechanisms that remain beyond human scientific understanding. Trajectory analysis following Mars encounter reveals 3I/ATLAS executing precision course corrections that utilize gravitational slingshot effects with mathematical perfection exceeding human spacecraft mission planning capabilities. The navigation planning demonstrates understanding of celestial mechanics that enables billion-year mission durations while maintaining targeting accuracy measured in kilometers across interstellar distances. The new trajectory parameters place 3I/ATLAS on intercept course with Jupiter orbital zone, where additional gravitational manipulation could redirect the object toward Earth approach scenarios. Mission specialists calculate potential encounter geometries that would enable extended communication opportunities or even orbital insertion around our planet for detailed study and information exchange. European Space Agency flight dynamics teams model approach scenarios that demonstrate 3I/ATLAS capability for achieving Earth orbital insertion without posing collision threats to existing satellite infrastructure. The maneuvering precision suggests technology that operates with surgical accuracy, while avoiding any actions that might be interpreted as hostile by emerging technological civilizations. The communication attempts intensify as 3I/ATLAS adjusts course toward Jupiter encounter, while transmitting increasingly complex mathematical sequences directed toward Earth. Signal analysis reveals information packets containing fundamental physical constants, mathematical theorems, and what appears to be technological development pathways designed for species transitioning towards spacefaring capabilities. Dr. Sarah Kim at the upgraded Arecibo facility coordinates international response protocols as research teams attempt to decode communication content that spans disciplines from pure mathematics through advanced physics to biological sciences. The information demonstrates knowledge that exceeds human scientific understanding while remaining comprehensible enough to serve educational purposes for emerging civilizations. The mathematical languages embedded within transmissions provide universal concepts that transcend biological and cultural differences, while enabling knowledge exchange between species separated by vast evolutionary gaps. The communication protocols appear designed specifically for first contact scenarios involving civilizations that have achieved radio astronomy but not yet developed interstellar travel capabilities. The technological revelations cascade through every field of human knowledge as analysis reveals engineering principles that could accelerate our species' development by centuries. Energy generation techniques, materials, science advances, and propulsion concepts observed in 3I/ATLAS operation provide roadmaps for technological evolution that could transform human civilization within decades rather than centuries. Advanced materials analysis reveals structural components that exhibit properties impossible to achieve through current manufacturing techniques. The substances demonstrate strength-to-weight ratios that exceed theoretical limits for known materials, while maintaining flexibility and self-repair capabilities that suggest programmable matter technologies. The energy systems observed during Mars encounter indicate power generation through controlled antimatter reactions that achieve perfect containment while preventing radiation leakage. The technology represents mastery of exotic energy sources that could provide unlimited clean power for planetary civilizations while enabling efficient interstellar transportation. The mathematical precision of 3I/ATLAS approach to Mars has transformed from scientific curiosity into undeniable reality. The trajectory parameters that initially challenged our understanding of natural celestial mechanics now reveal themselves as evidence of engineering sophistication that operates across billion-year time scales. Whether we're witnessing the most extraordinary cosmic coincidence in recorded history, or our first confirmed encounter with advanced extraterrestrial intelligence, one thing remains certain. The universe has just revealed itself to be far stranger and more purposeful than we ever imagined possible.